All right, so today we are going to do two different comparison tests, which are used whenever the series you're looking at doesn't really fall into any particular category, but it almost does. Like it's really close to being a geometric or really close to being a P series, and you can compare it to one of those and then make your conclusion based on that. And geometric and P series are the two that you're going to compare to most often, which is why I did want to leave this up here on the board so that you can look back at that. So the first kind of comparison test is direct comparison. So you're going to have two series that you're comparing. And so we're going to say that A sub n is smaller than B sub n. You have to figure out which one is smaller than the other. So if B sub n converges, then A sub n does too. Which should make sense. If this is the larger one and it converges, then the smaller one is also going to have to converge because it's smaller. Does that make sense? Okay. And so if A sub n diverges, then B sub n does as well. Which again should, like, it's logical, right? If the smaller one diverges and this one's bigger than that, it's going to diverge too. But you have to worry about which one's bigger and which one's smaller when you're comparing them. Let's just try a few. And so again, the way that you know you want to use a comparison test is if the series you're looking at doesn't really fit into any of the particular categories, but it's like it almost does. Like that almost looks like a P series, and then you can compare it to one. Now, you have to keep, whenever you do a comparison, you have to keep like the most important part, like the who's in charge part here. So we are going to compare this to and what's the part that we could like leave off? Like it's sort of rendered insignificant, like we don't really need to look at that part. Yeah, that like +2, do you know what I'm talking about here? Because the exponential part, that's like the really crucial, like who's in charge part. But that 2, you can leave off. So we're going to compare it to this series. Because that one, we can say some stuff about. What kind of series is that? Maybe if I rewrite it, it is geometric because you can write it as 1/3 to the n. So let's make a conclusion about that one, and then we'll be able to go back to the original one. So does that one converge or diverge? It converges, right? All right, converges because geometric with r equals 1/3, which is smaller than 1. So it converges because it's geometric and our R value is 1/3 and that's smaller than 1. So we made a conclusion about that one. Now we're trying to say something about this one. So if this one converges and we want to try to say that this one converges too, this has to be the larger one. Like this has to be, if you want to use A and B, this has to be the B sub n. Do you see what I'm saying there? Like if this one converges and we're trying to say this one does too, we have to say that this is smaller. All right. So we're going to say 1/2 + 3 to the n is smaller than 1/3 to the n for n bigger than 1. Now, is that true? Like you want to think, good, why is that true? Good, the bigger denominator, good, you're using the words I say too. The bigger denominator, the smaller the fraction. So that is true And so our overall conclusion to the whole thing would be that this converges by direct comparison. But it's tricky because you have to figure out which one is larger or smaller than the other one. Let's try again. So when you see that, you want to think, oh, I can compare that to something that I can answer very easily. What part of this can we kind of like leave off? Yeah, the 4. So we're going to compare this. You're basically leaving off the like insignificant part. Like you have to keep the important stuff. Like that n squared is the like who's in charge part here. So we're going to compare that to the series 1 over n squared. Because that we can say something about fairly easily. So what conclusion can we draw about that one? Because good, it's a p series and p is bigger than 1. So converges because p series with p equals 2, which is bigger than 1. So if that one converges, we're trying to say that this one converges too. So that means this has to be the larger one. Like we said, this one converges, so the smaller one's going to converge too. So we have to say this 1 over 4 plus n squared is smaller than 1 over n squared for n starting at 1. Yeah, no, the larger denominator is the smaller fraction. No, I knew exactly what you meant. So like, is that true? Because sometimes you go to write that and it's not true. I'm going to show you one like that in just a second, because then if that doesn't work, it's kind of like back to the drawing board. But in this case, that is true. And so what's our big like conclusion to the whole problem? It converges by direct comparison. All right, so let's try one more. And so if you compared it to something that diverged, you would want to try to prove that that's the smaller one, because if the smaller one diverges, then the bigger one does too. So what would you want to try to compare this to? Good, 1 over square root of n. You're basically just leaving off that plus 2. And again, you're trying to compare it to something that's easier, like you're trying to make an easier problem for yourself. So what do we know about that one? Good, p is a half, which is smaller than 1, so we get to conclude that it diverges. Good. So diverges because p series with p equals a half, which is smaller than 1. See, like when you boil it down like that, this doesn't seem that hard, but the problem is that like it's so much to remember because there's so many different tests. Like when we do them one at a time, it's just fine, but then it's like when they're all mixed up, it's really hard. You have to stay very organized inside your brain. All right, so here's the thing. Since that one diverged, we're trying to say that this one diverges too. So we want to try to say the one we compared it to is the smaller one. See what I'm saying? Like if this one diverges, that one is as well. So we want to say that this 1 over square root of n is smaller than 1 over 2 plus square root of n for n starting at 1. However, that's not true, right? And you can't draw a whole big conclusion based on a false statement. So now we're back to the drawing board. Like that didn't work. See, this is where this test kind of frustrates me because you did all of that and the exams, the AP exams timed, and now you have to like completely start over, right? So instead, we're gonna compare to just 1 over n. And I know you're like, well, you took off the square root. Yeah, but it's close enough. Like we're just doing a comparison. And that's going to also diverge because why? Good, because p is 1. Good. P equals 1. Or they'll even take that. Like if you say this is the harmonic series, because that's like a known one. Okay, so again, since that one diverges, we want to say that's the smaller one. So we're going to say 1 over n is smaller than 1 over 2 plus square root of n for n bigger than or equal to, actually, you know what, that might not be true bigger than 1, but as long as it is eventually, then we'll be okay. Let me see, would it be for 1? No, but it will be eventually. Let me see. Because if you plug in 1 isn't smaller than a third. But eventually this will be smaller. Let me see what n it will start with. I think it'll be 4. Because you would have a fourth less than or equal to a fourth. Yeah, there we go. Less than or equal to a fourth. It doesn't matter that we didn't start at 1 as long as it's true eventually. Because remember, we're going out to infinity. So as long as it's eventually true. Okay, so finally, what's our big conclusion to the whole thing? Diverges by direct comparison. I know, and see, that's why, and like, I'm not trying to really influence you one way or the other. If you like this, that's totally cool, and you're not wrong, and it's totally valid. I personally don't, because I like stuff that works the first try every time. I don't like that trial and error, unless like that's just sort of how the problem is. I like something that's going to work every time. So go ahead and flip over, and I'll show you the other one, which is the one I use if I have to do a comparison, which is called limit comparison. This one is like slightly more writing, not much, like very, very slightly more writing, but it's going to work every time. So like that, because that one we did that just didn't work, that ended up being a lot of writing because we had to like scratch out what we had and completely start over. So that's where my personality is. I would do this every time, even though it's like slightly more work. You'll see what I mean. All right, so if, now both of your series need to be positive. And they did for the other one too. It was 0 smaller than a sub n, smaller than b sub n. So if those are both positive and the limit as n goes to infinity, a sub n over b sub n, and it doesn't matter which one you put on top. It could be b sub n over a sub, like it doesn't matter. You just stack them one over top of the other. As long as that limit is finite and positive. Basically, as long as you get an answer. Then both series converge or both series diverge. So it's like the other comparison test and like the integral test, like they both do the same thing. So you do have to do that limit and work it out, but it kind of goes, you'll see after we do a couple, it kind of goes the same way every time and you get stuff that cancels out and it's really not too bad and it will work every time. So that's why I kind of like this one better, is my opinion. But these problems just look intimidating. Like you look at that and it's like, first of all, there's a sigma. So like right off the bat, it's like, ah, and then there's a square root of n over an n squared plus 1. Like I get it, like the problems just look terrifying. So what part of that can we like leave out when we do our comparison, like the insignificant part? Yeah, leave that out. All right, so we're going to compare this to that whole thing except the +1. Now I would like to reduce that a little bit. The square root of n, that's n to the 1/2. So if you have a power of 1/2 in the numerator, 2 in the denominator, it's 1/2 minus 2. It would be 1.5, but it's going to be in the denominator. So it is going to look like this. 1/n to the 3/2. Or you could think of it like 2 minus 1/2, 3/2, 1.5. I don't know, whatever. Anyway, it's just true. So again, the whole point was to compare it to something that we can easily make a conclusion about. That's a P series. So is it going to converge or diverge? It will converge because it's a P series with P equals 3/2, which is greater than 1. Good. So here's the goal. Since that one converged, we're trying to say that the other one does too. And so what you're going to do is that limit, and just as a heads up, it's going to look like a complete disaster. It's going to be a weird fraction with stuff everywhere, but it works every time. So that's why I like to go with this one. So we're going to do limit as n goes to infinity. Again, it doesn't matter which one goes in the numerator and which one goes in the denominator. Like take your pick, it really doesn't matter. I'll put this one over this one. But you take whatever the problem was over the one you compared it to. So whatever the original problem was over the one you compared it to, or the other way around. Again, it doesn't make a difference. And I understand that that looks awful, which is why limit comparison kind of turns some people off because they're like, oh, that looks terrible. But what's going to cancel? The square root of n's are going to cancel. I still usually write it out. You can write as much or as little as appeals to you. But I want to show you guys like mathematically what is happening. You're multiplying by the reciprocal. So you're going to flip this over. And that's why the square root of n's cancel. Also, just by way of foreshadowing, next class, we're going to do something called the ratio test, where you do this, a limit like this, a lot. So you're going to have to get used to a fraction over another fraction and then flipping it. That's like what a ratio is. So just as a heads up, I'm letting you know. So we said these cancel, and then you're doing the limit as n goes to infinity. So you have an n squared in the numerator and n squared in the denominator. That's a tie. So what are we going to use? Coefficients, which are both 1. So this comes out to 1. Most of the time it comes out to 1. But the point is that is finite. And so our big conclusion is converges by limit comparison. You do not need to say this is positive and finite. You showed it came out to 1. It's positive and finite. Do you know what I'm saying? Like you don't have to write that. That's like that's considered obvious enough that you don't have to say it. Yeah. I mean, you can if you want to. Sometimes the hardest part is picking what you want to compare it to. Again, you want to compare it to something that you can easily make a conclusion about, like something that's not going to cause you any problem. So what can we leave out of that as insignificant? Because there's actually 2 things. Yeah, you can leave out the -2 and you can leave out the 4, basically all the numbers. You keep the variables, you're good. So we're going to compare this to 1 over square root of n. You're basically like trimming off all the excess, like and just boiling it down to like what's actually going on. That's one we've already brought up, I'm sure, because these all tend to turn out the same. But that's a P series where P is a half. So this diverges because P series with P equals a half, which is smaller than 1. So here's the goal. Because that diverges, we're trying to say the other one does too. And you do that by showing this limit, which again, it's going to look like a disaster. So just buckle up. Limit n goes to infinity. It doesn't matter which one you put on the top and which one you put on the bottom. I usually put the like actual problem on the top and then over the one I compared it to. But again, it doesn't make a difference. And again, if you can do this part in your head, that's totally cool. I always write it out because I just like to see it. But you're multiplying by the reciprocal. This is getting flipped over. Nothing like cancels there, but we are doing the limit as n goes to infinity. So again, the powers are the same. They're both square roots, so the powers are both a half. That means you use the leading coefficient. It's kind of tricky because it's not 1/4. What does it come out to? Half. Why is it a half, not a 4th? Because you have to square root the 4. So it's going to come out to half. But the point is, that's positive and finite. You don't have to say that. It's like, duh, it is. So your whole conclusion is not converges, diverges. Phew. Does the same thing. It doesn't always converge. You're just saying it does the same thing as whatever this one did. Wait.
So if it's positive and finite, then it does the same exact thing
as the other one. So whatever this one did, that's why I was saying we found this one diverges. So our goal is to try and say the other one diverges too. It's like the integral test, like whatever the integral does, the series does too. And like, oh, well, see, that's where the direct comparison, that's why I don't like that one as much, because you have to show that one is smaller than the other and then it like makes the difference. But no, this one, it's whatever the one you compared it to does, this one does too. Converges or diverges, either way, you're just saying they both do the same thing. I can't think of one because in that case, you would probably be using a different test. Like if actually, if that were the case, you wouldn't even try to do a comparison. You would be doing the ratio test already, which is what I'm going to teach you next time. So it just wouldn't even come up because you just wouldn't even be doing this test. I can't think of a time that it would. That's why I like this one. Because it's a little bit more writing, but not much, and it works every time. So I like stuff that works every time. What's one? It's on there. Also, and you'll see this in your homework. And I actually kind of like these questions because you don't have to actually do anything. They won't give you an actual problem. They'll just say, this series is smaller than this one. This one converges. What can you conclude? And then it would be like, well, that one converges too then, or that one diverges or no conclude. Do you get what I'm saying? Like, you don't have to actually work it out. Yeah. All right, so this is like who's in charge here. We're going to take the most important parts, which means we're basically going to leave off that +1 and the 4. So we're going to compare 2. And let's see, I would have that 2 to the n in the numerator. Now, if we have an n in the numerator and an n cubed in the denominator, how can I simplify that? N squared, good, and perfect. That looks really weird. Well, or cool. It's 2 to the n in the numerator and n to the 2 in the denominator. Kind of like- So yeah, like if you cut away all this excess, you have n over n cubed, and then that'll reduce to n squared. Now that's not geometric, and it's not a p series either. So look behind me at all this recap that we did. And again, you want to go for something easy. That's the point of the comparison, is you're comparing it to something you can do a pretty easy test for. Good, nth term test. We're going to do limit as n goes to infinity of this. And because the numerator is exponential, the denominator is polynomial, the numerator grows way quicker. Good, so where is this going to head? Infinity. Perfect. So diverges by nth term test. So again, and I feel like this is an aha moment for a few of you, because that one diverged, we're trying to say that the original one diverges too. Again, they just do the same thing. And so we're going to do this limit. And again, it does not matter which one goes on top and which one goes on the bottom. I just usually put the actual problem on top and then the one that I compared it to on the bottom. And again, just as a heads up, next class when we do the ratio test, like that is a ratio, something over something else. Every single problem is going to look like that. It looks super intimidating. Just remember, you're going to multiply by the reciprocal and then some stuff is going to cancel out. Like something is always going to cancel or reduce. And again, I write that every single time. If you can do some of it in your head or you're cool with skipping that first step, like that's totally up to you. I write it. I know it's a lot to write, but then I don't lose track of what I'm doing. So what cancels? The 2 to the n's cancel. Now I probably wouldn't write anymore after this. You can if you want. You've got n cubed in the numerator and 4n cubed in the denominator. So you're going to use the coefficients. And so what would it come out to when you do this limit? 1/4. And the point is that is positive and finite. So what's our conclusion? Good. Bless you. So again, whatever that one does, the other one does too.